Good afternoon. Myself Dr. P.R. Krishnaveni, Associate Professor of Chemistry, Sasi Institute of Technology and Engineering, Tadapalligudam. Today I am going to start Unit 3 of the course Engineering Chemistry. So Unit 3 of Engineering Chemistry course is Chemistry of Materials. So Unit 3 is Chemistry of Materials. So before going to discuss about this unit, I will tell you the objectives of this unit. The main objective of this unit is to express the demand of the various engineering materials that have wide engineering properties. And not only that, to classify and discuss the advanced materials which are used in different industries like manufacturing industries, steel industries, construction industries, so on. So now coming to Unit 3. This unit is divided into two parts, Part A and Part B. Part B consists of nanomaterials. Part A is nanomaterials and thermal analysis techniques. Part B is refractories, lubricants and cement. So coming to the nanomaterials part. So here first we will discuss about the introduction. So in introduction we will basically concentrating on the types of the nanomaterials, that means one-dimensional nanomaterials. We will discuss two-dimensional nanomaterials and three-dimensional nanomaterials. After that we will discuss about the approaching methods for nanomaterials, that means in what way we can synthesize the nanomaterials. So there we will be discussing about the two approaches, top-down approach and bottom-up approach. So in top-down approach, we will be discussing about the Sol-Gel method and chemical reduction method. After that we will discuss about the characterization methods. In characterization method we will discuss about BET method. BET method means Bronner-Emmett-Teller method. This method is mainly used to analyze the surface area of a material and pore size of the material. And the other methods are SEM, scanning electron microscopy, and TEM, transmission electron microscopy. We will explain this by taking the example of titanium oxide. After that we will discuss about the applications of graphene and fullerenes. Graphene is the basis for the carbon nanotubes. So later we will discuss about the types of carbon nanotubes, preparation and the applications of carbon nanotubes. And the next one is thermal analysis techniques. So in thermal analysis technique, we will discuss about the instrumentation, applications of thermogravimetry analysis, differential thermal analysis, differential scanning, colorimetry. So coming to the Part B. In Part B, the first topic is refractories. A refractory is nothing but the material which is not easy to fuse. So refractory means what? A material which is not easy to fuse. Easy to fuse means it cannot be easily melted. Why it cannot be easily melted means its fusion temperature will be high. All that we will discuss in the case of definition. Next one is classification. So here refractories will be classified basing on the fusion temperature and basing on the chemical composition. All that we will discuss here. So coming to classification, we will discuss classification based on fusion temperature, and next one is classification based on chemical composition. So based on fusion temperature, refractories will be classifying as normal refractories, high refractories and super refractories. And basing on chemical composition, we will be classifying as organic refractories, acidic refractories, basic refractories and neutral refractories. After that, we will discuss about the properties of refractories and the reasons for the failure of refractories. And the next one is lubricants. So in lubricants, basically we will be discussing the definition. A lubricant means what? How we will be defining? It is nothing but a material which reduces the friction when applied between two surfaces. When the lubricant is applied between two surfaces, it reduces the friction between the two surfaces. Next we will discuss about the mechanism of lubricants, properties of lubricants. And the last topic of this unit is cement. So in cement we will discuss about the various constituents of cement, manufacturing process of cement and the parameters to characterize the clinker formation. So what are the parameters means? Lime saturation factor, silica ratio, alumina ratio, chemistry of setting and hardening, and next we will discuss the deterioration of cement. Coming to the outcomes of this unit. So at the end of the unit, the students will be able to synthesize the nanomaterials for modern advances of engineering chemistry. They will be able to summarize the techniques that detect and measure the changes of state of a reaction, and they will be able to illustrate the commonly used industrial materials. So this is about the syllabus what we have in the unit 3 of engineering chemistry. So now coming to the first topic of unit 3. So coming to the first topic of unit 3, in first lecture I am going to cover the introduction and sol-gel method. So coming to the introduction. So coming to the introduction, nanomaterials means these are the materials which have the dimensions in nanometric scale. As we all know, nano means what? A tiny or small particle. So nano means what? 1 billion of a meter in physical scale or length. So nanoparticles means how we can define means these are the particles within the size ranging from 1 to 50 nanometers. And these can be defined as the objects or materials that have size decreased to nanoscale. And these materials exhibit some distinct properties when compared to the properties of the material in bulk form. So these are the various nanoparticles. So here I have showed you the nanoparticles classification as organic particles and inorganic particles. So organic nanoparticles means what are the examples we can say? Dendrimer, layered biopolymer, liposome. Inorganic nanoparticles means carbon nanotubes, mesoporous silica, gold shell, organic oxide shell, quantum dot. And example for hybrid nanoparticles is hydrogel. Later I will show you the same classification as one-dimensional, two-dimensional and three-dimensional nanoparticles. So coming to the physical properties of nanoparticles. The main physical properties are size, shape and surface area, surface morphology or topography, size distribution, aggregation state, and the size including crystallinity and defect structure, solubility. These are the important physical properties of nanomaterials. Next, coming to the chemical properties. So the main chemical properties are structural formula or molecular structure of the nanoparticle, composition of the nanoparticle. Composition of the nanoparticle means including the purity of the nanoparticle or the additives or the impurities. Phase identity, surface chemistry, that means its composition, charge, tension, reactive sites, physical structure, photocatalytic properties, zeta potential, hydrophilicity and lipophilicity. So these are the main chemical properties of the nanoparticles. In addition to this, there are some other properties like mechanical properties, optical properties and electrical properties. So that we will discuss now. So the other properties are, up to now we have discussed about the physical properties of nanoparticles, chemical properties of nanoparticles, and the next properties are mechanical properties, optical properties and electrical properties. Coming to the mechanical properties. So mechanical properties means these are the physical properties that are exhibited by applying force on the nanoparticles. So what are the properties means? Tensile strength, modulus of elasticity, elongation, ductility, rigidity, etc. So these are the some of the mechanical properties of the polymers. Coming to the optical properties. Optical properties means reflection of light, absorption of light, emission and transmission. These optical properties are dynamic and they show these properties significantly differ from the materials of the same bulk form. So the optical properties exhibited by the nanoparticles are dynamic and they significantly differ from the bulk materials. And coming to the electrical properties. Electrical properties means conductivity or resistivity. Conductivity or resistivity will come under electrical properties. So these electrical properties, they will alter with size, alter with size of the nanoparticle. They will alter with the size of the nanoparticle. And that means this you can understand with this example. So for this one I am telling you the example. For example, if you take a ceramic material, for ceramic material, conductivity will increase with decrease in nanoparticle size. with decrease in nanoparticle size. So this is the case with the ceramics. For example, second example, if we take a metal, coming to the metal, conductivity will decrease with increase in nano size or nanoparticle size. So this is about the electrical properties of the nanoparticles. Now I will show you the deviation of the properties with size of the particles. For example, if we take particle copper, so it is opaque when it is in bulk form. It is transparent when it is in nano form. Platinum, when it is in bulk form it is inert, but when it is in nano form it acts as a good catalyst. So that's why while using the discussing the catalytic properties, we will be saying that nanoparticle sized platinum or gold will enhances the catalytic reaction rate. Aluminium, when it is in bulk form it is stable, and when it is in nano level it is combustible. And gold exists as solid at bulk level and it exists as liquid at nano level. And silicon will act as insulator in bulk form, and in nano form it acts as conductor. So these are some of the particles and how the properties will be changing when a bulk material is changed to nanoparticle size. Next, classification of nanoparticles. So nanoparticles can be classified as one-dimensional nanoparticles, two-dimensional nanoparticles and three-dimensional nanoparticles. As we all know, one-dimensional nanoparticles means here the nanoparticles here the atoms will be arranged as one-dimensional pattern. That means these are the nanoparticles where there will have one-dimensional arrangement. In short, what we can say? One-dimensional arrangement of atoms. And examples are nanofibers, nanoporous fibers, nanotubes, etc. Two-dimensional nanoparticles. So these nanoparticles, examples. Here two-dimensional nanoparticles means nothing but what? Here the atoms will have two-dimensional arrangement. So examples are nanosheet, nanoporous sheet, nanoplate, etc. Three-dimensional network. Three-dimensional nanoparticles means here three-dimensional arrangement will exist. And examples for three-dimensional nanoparticles we can take as mesoporous materials, metal organic framework, nanostructure assembly. Now I will show you the pictures of these examples. So see here. So for zero dimensional nanoparticles, examples are nanosphere, core shell, York shell. And for one dimensional, nanofibers, nanoporous fiber, nanotube. For two dimensional, nanosheet, nanoporous sheet, nanoplate. For three dimensional, mesoporous structure, metal organic framework, nanostructure assembly. Next topic is approaches to nanomaterial synthesis. So for synthesizing nanomaterials, we can use top-down approach or bottom-up approach. Here top-down approach means here we will be taking a bulk material and this bulk material will be transformed into nanoparticle size. So here we can transform either by using physical methods or mechanical methods. In bottom-up approach, we will start with the materials which have size less than the nanoparticle. That means here we can start with atoms or molecules. Now these will be made into nanoparticle. How means we will be placing atom by atom, molecule by molecule or cluster by cluster. So see here. Here top down approach means what I said, we will take a bulk material. So that bulk material will be converted into nanostructure. How means by making into fragments or else by etching also we can do. Coming to bottom up approach, what we are doing? We are starting with the atoms and these atoms will be formed as clusters and these clusters will be converting into nanostructure. So you can understand in detail if we discuss them separately. So top down approach means what I have said, we will start with the bulk material and we will convert that into nanoparticle size. So here the starting material is solid. Coming to bottom up approach method, starting material may be liquid or gas. Coming to the processing methods, we can use mechanical methods, or physical methods. Or this can also be called as lithographic methods. Photolithography, it is better to write it as Lithographic methods. Photolithography, electron beam lithography. Physical methods. Physical methods means by etching, cutting, or by grinding. Or by ball milling. So these are the processing methods for top down approach. So now coming to the processing methods for bottom up approach. The processing methods are physical methods, and second one is chemical methods. Physical methods means we can take physical vapor deposition. Physical vapor deposition means here condensation of vapor species takes place. Condensation of vapor species. So what are that methods means? Sputtering, evaporation, plasma arc, laser ablation. Coming to the chemical methods. Chemical methods means chemical vapor deposition. Here deposition of vapor species. So the methods may be sol-gel method, pyrolysis, electrolytic deposition. So this is the brief description about top down approach and bottom up approach. So now coming to the sol-gel method. The sol-gel method comes under bottom up approach. So this method involves evolution of inorganic network through the formation of colloidal suspension, that is nothing but sol, and gelation of the sol to form a network in a continuous liquid form, that is called gel. So the precursors nothing but the starting materials. Starting materials in sol-gel method are metal alkoxides or metal chlorides. So these metal alkoxides or metal chlorides, they will undergo hydrolysis and polycondensation reactions. During hydrolysis, sol will be formed, and during polycondensation reactions, gel will be formed. So this process we will discuss now. So the various steps involved in sol gel method are sol formation, gel formation, drying process, calcination and heat treatment. Coming to the first one, sol formation. In sol formation, what happens means metal alkoxides, they will undergo hydrolysis. Hydrolysis means what? Reaction with water. So this is the metal alkoxide. So this will react with water and forms sol. So this hydrolysis results in the formation of sol. Next, gel formation. For gel formation, condensation reactions takes place followed by polycondensation. So this results in the formation of gel. Here, water condensation can take place, or alcohol condensation. So water condensation results in water. Alcohol condensation results in the formation of alcohol. So here so it will undergo condensation, sol will undergo condensation and forms gel like this. So here water is being formed. Next what happens means this will undergo polycondensation and forms metal oxo compounds. Alcohol condensation means MOR plus, it results in the formation of gel like this. So this is the gel and here we are getting the alcohol. Next one is drying. Drying process means nothing but the removal of pore liquid. That means the liquid existing between the pores will be removed. Here, if drying is done under hypercritical conditions, what happens means the network will not collapse and it will form aerosols. So under hypercritical conditions, the network does not collapse and forms aerosols. Under ambient conditions, the pores will shrink and forms xerosols. Now I will show you the structures of this aerosol and xerosol. So see here. So this is how the xerogel is formed and this is how the aerogel is formed. That means under hyper conditions aerosol will be formed and under ambient conditions zero gel will be formed. Next, calcination. Calcination means nothing but the process of heating a material to high temperature but below its melting point. That means here what happens means thermal decomposition takes place. That's why here what we'll do means they'll take a zero gel and they'll heat this one to 800 degrees centigrade. As a result, what happens means the pores here, whatever the pores are there, that pores will be collapsed. And finally what happens means gel decomposition takes place. So here the zero gel will be heated to 800 degrees centigrade. As a result, the pores will be shrinked and collapsed and the organic molecules will be vaporized and finally gel decomposition takes place. Next, heat treatment. This heat treatment is done to give the desired shape to the nanoparticle. Gives desired shape to the nanoparticle. That means we can convert that nanoparticle into a fiber form or in the form of films or as nano powder. Subsequently these will be transformed into ceramic. So this is about the Sol-Gel method of preparation of nanoparticles. Next, advantages. Coming to the advantages of the Sol-Gel method, this method is cheap and operates at low temperature. And next, very thin metal oxides can be formed. That means very thin metal oxides can be prepared. And this method is a better alternative method to prepare glass. And using this method we can prepare bulk materials, nano powder, fibers, films, all these can be prepared. So these are some of the advantages of Sol-Gel method. Next, limitations. The limitations of this method are, here the bonding is very weak. Next, low wear resistance. High permeability. Substrate dependent. Or we can say substrate dependency. Difficulty in controlling the pore size. So these are the limitations of Sol-Gel method. And now the present researchers They are mainly concentrating on biomolecules from sol gel matrix, bioactive nanocoatings for future generation, organically modified sol gel sensors. So these are the future applications of this sol gel method. Thank you.